The following program is brought to you by Caltech.
All right, our third speaker will be Richard Lyon, research scientist, Google Incorporated. Very brief introduction again. Most noticeable thing, he is the inventor of the optical mouse. Day to day, every day, next time you use it, you remember Richard Lyon. He had his bachelor's degree in EAS, actually, in 1974. And he has many honors. He is a fellow of the IEEE. At the moment, he is a research scientist at Google. And he is leading the group on machine learning, right? Machine learning research, basically. So, welcome back.
Yeah. So it's kind of a two topics mashed together here, and the connection between them on machine hearing and the legacy of John R. Pierce. Pierce, I was happy to hear, was mentioned by at least 4 different speakers yesterday in various different contexts for things he had done at and after Caltech. And I'll say a bit about him. I've been teaching a course at Stanford this fall in human and machine hearing. And I like to do that by talking about the history and the people that came up with the various ideas. I think it gives people a way to get a handle on the ideas and the thought processes and evolutions that led to those ideas. So these are some of the slides I have in my typical introductory presentations. One of those is this slide that shows the unrolled cochlea in a figure from a 1976 paper by Zweig, Leipz, and Pierce. So these are 3 Caltechers. George Zweig, the physicist, John Pierce was a professor of electrical engineering here at the time, and their student Richard Leipz working in the lab there in 35 steel, the same lab I used to work for John Pierce in myself when I was an undergraduate. And this particular paper, probably of all the things that got me into the machine hearing field and how to think about how to analyze the cochlea and hearing and so forth, this particular paper was, I'd say, the most influential. And they basically applied fundamental mathematical techniques that were more common among the physicists, the WKB method for solving wave propagation equations in non-uniform media. They applied that to the cochlea, and this led to some early digital signal processing-based models of hearing that I worked on at Xerox and Schlumberger, and then it led to the work that I did with Carver Mead and his lab here in the 80s on an analog cochlea chip. And it's still the basis for some of the newer cochlear models that we're using actually in production now at Google. Here's a picture of John from the front of a Caltech document of an oral history interview that was done with him back in '79. You'll notice that John was born in 1910, the same year as the Caltech EE department, which is one of the reasons I chose to make this connection. 8 years ago he died, but he would be 100 this year. I'll say a bit about his trajectory. He came to Caltech and got his bachelor's degree in 1933 and a PhD in 1936. He said this was a great time to stay in school because it was in the depth of the Depression. And he hadn't, I think, intended originally to stay here for a PhD, but there wasn't much else to be done at the time, so he did. And then he went off to work at AT&T Bell Laboratories, where he stayed for 35 years and got to be one of the executive director of research there at the end. And he retired and came to Caltech in 1971. I was a freshman the year 70, 71, and he came in the later part of that year, I believe. So I got to meet him. I was looking for a summer job, and Hardy Martell said, well, you should go talk to this new guy, John Pierce. He might need some help. So that's how I got hooked up with John. While he was here, he did a lot of things. He became the chief technologist for the Jet Propulsion Laboratory. He was, I think, involved in recruiting Ivan Sutherland to come here, and with Carver Mead starting the computer science department. And in 1983, he moved up to Stanford and stayed there for quite a while, working in the computer music group, which he really rejuvenated. He was kind of a father figure and sort of the patron for that group. It turns out he did a lot to start the field of computer music. I'll say, I don't know if I have any more about that later, but I have heard a story one time from Max Matthews, who's still working at Karma, the computer music lab up there. Max went to a concert with John Pierce one time in 1959 when he worked for him at Bell Labs, and afterwards Max said, "I could make better music than that with a computer." He didn't think much of the concert, and Pierce said, "Well, why don't you go do that?" And that's how computer music was born right there. Pierce was good at making snap decisions and going with his gut. He, for some reason, apparently when he was at Caltech, he got fascinated by all things Japanese when he was here early on. And when he came back here in '71, he bought this Japanese-styled house down just south of the campus on Canyon Road with a koi pond and everything. Sometimes when he would go away in the summer, he needed someone to look after the koi, so that was my job as well as working in the lab. So I'd go over there and take care of the fish. And, later, when he moved up to Stanford, and I went to dinner with him and his wife Ellen before she died, she first didn't recognize me and looked at me and second glance and said, "Oh, I understand." She said, "I've never seen you with shoes on before." So, John's early work was all in vacuum tubes and electron ballistics and stuff like that. He did a lot of really interesting work in that area. One of the papers I'll mention later is this 1943 paper on transmission line equation in terms of impedance. This was a way to analyze a non-uniform wave transmission in a non-uniform medium. A lot like this cochlear problem that he solved at Caltech many years later with George Zweig, but a rather different method. There's a figure from the later paper, but he had a figure just like it, except that he had an inductor and a capacitor in there instead of the more generalized form. The methods he came up with in the early paper were great for one-dimensional systems, but the methods they came up with applying the WKB method later gave same results for one-dimensional systems, but it actually would generalize better to multidimensional systems. So it was a great thing. But that's the kind of thing that he had these fundamentals in his mind for over long periods of time and would apply them to whatever problems came up. He's listed in the National Inventors Hall of Fame as the inventor of the communications satellite, and we heard yesterday from Harold Rosen about how he had basically predicted that a geosynchronous approach would not work. So it's not like everything he decided was exactly true, but he did put up the first couple of satellites that were used for communications. He was instrumental in NASA's ECHO satellite. That's what this citation talks about. It was a big aluminized mylar balloon in outer space, which I remember seeing as a child as it went by. It was big news that you could look up at night and see this new star moving across the sky. And then later, the Bell Labs built Telstar satellite, which had I'm pretty sure it used his traveling wave tube transponder, and it had some new transistors in it and various things. So that was the first active transponder commercial communication satellite. This is a photo of John on the left with Rudy Kampfner there at the blackboard, and Rudy was the one that actually invented the traveling wave tube, and John discovered him toiling away on it in a lab in England during World War II and recruited Rudy to come back to Bell Labs. John came up with the mathematics that led to the stable operation of these things and really understanding how they worked. The guy on the right is Harry Nyquist. You guys have probably heard of the Nyquist sampling theorem and things like that. So it was a good time for these guys at Bell Labs. And this quote, "Nature abhors a vacuum tube," is often attributed to John. There's one of his, holding one of his traveling wave tube amplifier vacuum tubes and a diagram of how the thing works. In 1956, he predicted that vacuum tubes would always beat transistors at high power, high frequency jobs. And I said here they still do, but then I heard Dave Rutledge gave a talk yesterday about his successful student startup Wavestream. They've now got 200-watt multi-gigahertz amplifiers running with solid-state devices. So maybe the days of the traveling wave tube are numbered. They do still, they are still the only solution for certain jobs with high frequency, high power, and high bandwidth. But maybe eventually John will be wrong on this. This quote about nature abhors a vacuum tube was actually the last line of it in one of his papers that I found. And he says, a friend of mine twisted an old aphorism into a new one and said, nature abhors a vacuum. So he never claimed this was his own saying. He attributed it to a friend of his. And later in a oral history at the IEEE site, he said it was Myron Glass who came up with that. But you can find lots of books, papers, and web pages, hundreds of them, that attribute it to John. But you know, he was always good about giving credit where it's due. I found this paper in an article written by Ed Posner, Rod Goodman, and Bob McLeese here in the Caltech News 1986. And it showed this portrait of John Pierce that was drawn by Sylvia Posner, and it was hanging in the Pierce Lab in Steele. I don't know if the Pierce Lab is still there. Does anybody know? And the picture is still hanging. Still in there? Okay. So by 1986, Pierce was kind of a memory at Caltech. He had been up at Stanford for a few years, which is Caltech's loss, but my gain, because I was up there and got to see John a lot, usually at the weekly hearing seminars at Stanford. A couple guys over the years organized these seminars, and I would go a lot. John would go a lot, so I got to see him frequently. And he, quite often in these seminars, he'd be sitting in a chair in the back of the room, and he'd fall asleep and maybe snore a little bit, but then somewhere in the middle or toward the end, he'd wake up and ask some incredibly cogent questions. And somehow he was taking it all in. He published a lot of things in the hearing and music and, to some extent, speech areas. In particular, these ones in bold, The Cochlear Compromise is the paper I mentioned, and another one in 1991 on periodicity and pitch perception that I'll say a few words about, which he actually did his own psychophysics experiments at the age of 80 at Stanford, in which he generated 3 signals. This one, called B in the middle, actually has a sign reversal in that little blip that's circled in red there. That makes the autocorrelation function of signal B match signal C, whereas the pulse rate of B matches A. And then the question is, do people hear this? What's the pitch of this thing? Does it sound more like A or more like C? And it turns out the answer is one or the other, depending on the parameters. And he did the experiments to map out that space and relate it to the dynamics of the cochlea and so forth. Very important work that has to do with models of hearing and kinds of stuff I do now. He used to have a lot of good sayings, like I came up with it the first time I saw it, or I thought of it the first time you told me, and things like that. It was his kind of way of saying that, you know, I adopt your idea and I give you credit for it too. And toys are a lot more fun since plastic. And things like artificial intelligence is real stupidity. That really didn't make him any friends in the AI community. His advice to me was to be smart, but also be lucky. And I think I've done some of that. Back at Bell Labs, he did some interesting stuff, like when the transistor was invented, he came up with the name for it. And coming up with the name transistor wasn't good enough. They had to write a memo and have a ballot before they could decide that was the name of it. So here's a copy of the naming ballot part of it, and it shows his suggestion there. I'm glad that we don't have millions of iotatrons these days. Transistor just rings better. It won by a landslide in that vote. He also did a lot on the whole trend toward digital media, like in this 1945 patent filing on a communication system employing pulse code modulation. He was basically teaching the world how to use digitization of voice signals in the telephone system and stuff like that. He wrote a very influential paper with Barney Oliver and Claude Shannon called The Philosophy of PCM, in which they explained all the incredible benefits of going digital. So Carver, this is another one you could have put in your talk last night about a Caltecher changing the world. This transition to digital was a big part of that transition to the computing and information economy that we have nowadays. So John was a part of that in his way. He had a lot of other contributions. He wrote science fiction stories under the name J.J. Coupling. He invented a thing called a Pierce gun that's part of a lot of vacuum tubes. In particular, it's a part of just about every linear accelerator nowadays. He invented reflex klystrons. He started the computer music business, and he did the work leading to the T1 digital carrier system for transcontinental telephony. Pierce loops was a computer networking scheme. Digital signal processing I threw on here because when I was a junior here, he managed to get me a job at Bell Labs. And he told the guys at Bell Labs they should hire me, and then they sent back a letter saying, well, why should we hire that guy? He's got less than an A in some important electrical engineering subjects. And he said, hire him anyway. So I got a job at Bell Labs. I learned a lot from the guys doing digital signal processing there. And then when I came back to Caltech as a senior, I taught what I'm pretty sure was Caltech's first course in digital signal processing. And among my students were 3 or 4 faculty members, Carver, and I think Chuck Welts was in there, and various people like that. So that was how DSP came to Caltech, at least in my version of the history. He did a lot of space science, as you know, with the satellites and the JPL work and so on, and he wrote a lot of books. Here's a couple of his books that connect to the machine hearing story, where he basically talked about how hearing works. So these were in 1959 and 60. I was telling Amnon last night, he also wrote a book called Quantum Electronics on lasers and transistors. That I had the date wrong on it. That was 1966, but still, he was very good at popularizing the science and making it easy to understand. These books were co-authored by his friend Ed David, who was another interesting character, and he connects to the machine hearing work largely through this paper he did on artificial auditory recognition and telephony. Back in 1958, he's already talking about how we can use automatic speech recognition in the telephone network to automate all kinds of functions. And the thing I like about it in particular is that, you know, my approach to machine hearing is to base it on human hearing and respect the auditory nerve, because we know an awful lot about how sound is represented there, and the cochlea does amazing things. And he had that ear and brain and auditory nerve thing as explicit part of his conception of how a thing would work at that time. And he showed how you could build a rule-based recognizer. This sort of foreshadows the artificial intelligence or rule-based system approach to recognition. This was for recognizing digits 1 through 9 and 0. He also showed a template-based approach where you could, these are binarized spectrograms from a work he was describing by a guy named Kirsta in 1947. The amazing thing about this is they actually built a digital speech recognition system in the 1940s, and they didn't use computers. They used IBM card sorters. They punched these spectra patterns into Hollerith cards, and they programmed the card sorter to do the matching against the template cards, which are the lower ones. So that was pretty amazing digital speech recognizer for the 1940s, I thought. But the speech recognition work comes back around through John Pierce in 1969. He wrote this paper called Wither Speech Recognition, which was withering commentary on the field. And I'm not sure what happened here. Did he have a falling out with Ed David? I don't think that was it. I don't know if Ed was the target of this commentary, but somewhere between this good stuff that Ed was doing in the 50s and this paper that John wrote in the 60s, his attitude toward that whole field went sour, because he used all kinds of negative terminology in here and impugned people's motives and all kinds of stuff. He did end the paper with some good advice about questions that one ought to ask themselves, and I've asked myself these kinds of questions from time to time, and I think it makes sense. And this really did help the field, I think, recover. And when the funding came back, when they recovered from the real stupidity and the wither speech recognition and so forth, they did start doing better work. So, where's this field going? Applications of sound analysis based on human hearing are increasing at a phenomenal rate. We have thousands of computers at Google analyzing sound all day, every day. All the YouTube video upload soundtracks, for example. And I'm writing a book on it called Human and Machine Hearing, Extracted Meaning from Sound, dedicated to John Pierce, out next year or the year after perhaps. And this is the title slide from my lectures at Stanford when I talk about this stuff. And it's all about connecting how the humans do it to how the machines do it in a way that makes it work well. Thanks.
I have a question, but we'll first take questions from the audience. Questions? Yes. Can you give the microphone?
Actually, I thought I would provide maybe an answer, and I'm not sure that my memory is correct. So if Bob is here, Bob McLeese, are you here? He could do a better job at this. But my recollection, which is hopefully correct, is that when we moved from Steele, the electrical engineering department moved from the Steele building to the Moore building in 1995. Uh-huh. And when we moved to Steele, the Pierce lab became the communication lab, which is where Bob McLeese's group and at the time Andrea Goldsmith were housed. And since in the same year, Ed Posner passed away, and I think it was then renamed to honor both of those men. So, but it's still there in the Moore building.
Yeah, it was really sad when Ed died. He had gotten me a job at JPL where I learned a lot and worked with Bob McLeese's group up there, and some great people.
Question? Yes, yeah.
So what is Google actually doing with hearing?
Well, I'd tell you, but I'd have to shoot you. Actually, we do a lot of things. When we analyze the soundtracks of YouTube videos, that's where a lot of my work is involved. There's a bunch of different kinds of classifications that we do. We add audio features to video features for some of those, and some of them are pure audio tasks. You know, the top-level decision you make when someone uploads something on YouTube is it pornography or not? After that, there's a lot of more subtle distinctions that we want to get at. Copyright violations, for example, so we have like audio fingerprinting and things like that. Most of the stuff is kind of buried in the underwear where the users don't notice it, but it makes various things work better in terms of organizing and searching videos. And we'll be exposing more of that functionality over time, but right now it's pretty much invisible to you. But we do analyze all the soundtracks of all the videos that get uploaded through explicit models of human hearing. Yeah.
That's a fair answer. Yeah, question there.
One of the courses that was offered here at Caltech when I was doing my undergraduate was cross-listed between EE and music. It was called Projects in Music and Science, taught by then pianist in residence James Boyk.
Yeah, I met James once. Interesting guy.
One of the themes that course had was giving the students an appreciation and an opportunity for experimentation, not just in the sort of the mathematics at a sort of a basic level or a kind of conceptual level, but also on a almost visceral level, an understanding of how their own hearing worked and what it was they were hearing, what it was they were reacting to. One of my projects as part of the class was an analysis of perceptual accuracy, of how much fidelity is being lost when we do things like compress music. With the work that you've been involved with in Stanford and so forth, the courses that you teach, modeling of the way that the human ear works, do you have any thoughts on sort of the role of academia in not just the biophysics of how humans hear, but the qualitative aspects, the potential for lossage, the cheapening, if you wish, by sort of a careless application of things like compression and information theory?
Yeah. The notion of things like objective quality measurement of sound is something that I think the auditory models are good for as a mechanism for getting at that. I haven't specifically paid much attention to that, but I know for the music aficionados, the ability to quantify the loss that you get in the so-called perceptually lossless coding, it's an important topic, and I think some of the students at Karma at Stanford are interested in that. So I'm hoping someone will follow up on that kind of idea.
Very good. Yes. Last question.
I'm kind of intrigued. Bob Bauer. I don't know where. I'm kind of intrigued with what you're talking about here, and I think of it in the context of what was the name of the chair of Cornell yesterday who was talking about visual things. And we all know that you can look at a picture and you look at it different ways, and you see totally different pictures. You could see Einstein, or you could see Marilyn Monroe. And I wonder if the same thing isn't possibly true with respect to sound and hearing.
Yeah, there are a lot of interesting auditory illusions that have counterparts in visual illusions, and some counterparts, some don't. But yeah, that's an interesting field, and like the idea of pitch, a sound where you can have a sound where the pitch is always going up, but it gets lower over time. I know that sounds paradoxical, but you can start with a high pitch and have the pitch always go up, and then later you have a low pitch. How did that happen, right? And barber pole illusions and things like that.
I then have to add, because my wife is Chinese, I wonder how that enters in with the Chinese where they have tonal.
Yeah, the question is how that relates to Chinese and tonal languages and so on. That's very much a higher level, speech kind of function, and speech is a fascinating application of models of hearing, but it's like going through several levels of cortical analysis. It's sort of like recognizing your grandmother is several levels away from primary visual cortex. Recognizing speech is several levels away from auditory cortex. I tend to stay away from those higher level functions and focus more on more of a bottom-up approach of simpler things, but the stuff we come up with definitely can be connected to speech recognizers and make those work better as well. I'm not into speech right now, but it's one of the things that we can do with this.
Very good. Thank you very much again.